Hi, welcome to lesson 14b, Limits at Infinity. The goal of today's lesson is to determine the limits of a function, or how a function behaves, when x gets very, very large. Like, very large. So, there's a bit of notation here. If we say as x approaches infinity, that means that x is getting very, very large in the positive direction. So more than 10, more than 100, more than 1,000, more than 1,000,000, more than 5, 10 billion, trillion, kajillion. It's like super, super large, and it's way out there to the right on the Cartesian plane. We also can write as x approaches negative infinity, and that of course would mean the x gets very, very large in the negative direction, like I'm saying, very, very, very large. So when we're talking about this kind of thing, we're saying that yes, x can get greater than 1, x is greater than 100, x is greater than 1,000,000, etc., etc., etc. We're also saying then that if we were to multiply x by certain things, we could say, well, if we had 2x or 3x, let's go 3x, 3x is greater than x. As a matter of fact, 3x is greater than 2x, because when you're multiplying 3 by a really, really large number, it's going to be greater than multiplying 2 by that really, really large number. If we had x squared, well, that's going to be larger than x. As a matter of fact, x squared is going to be larger than 1,000,000x, because x is very, very, very large and much, much larger than 1,000,000. So if we square that very, very large number, greater than 1,000,000, and compare it to 1,000,000 times that number, that's going to be much greater than that. Okay, so we're just talking about scope and how large values can be. So x gets so large that if we happen to have 1 over x, that is going to have that's a constant divided by a super large number, that's going to approach 0. It won't actually reach 0, but it'll approach 0. Okay, and then so we can then state this as the limit of 1 over x as x approaches infinity equals 0. Okay, it's the limit that equals 0 as 1 over x approaches 0, as x gets very, very large. So the limit can equal 0. That's not saying that 1 over x becomes 0. 1 over x is just approaching 0. Okay. So we're talking about limits when x is very, very large. So let's take a quick little example here. Suppose we've got this function h of x, and that equals 40 minus 3x all over 2x plus 5. Well, there's a few things we can find from this. This is what you call a rational function. We've got values in an expression in the numerator and the denominator. The restriction on this, well, we can't ever divide by 0, so our restriction is that 2x plus 5 cannot equal 0, which means that 2x cannot equal negative 5, therefore x cannot equal negative 5 over 2. So that's our restriction. And if x cannot equal negative 5 halves, then that tells us that the vertical asymptote is x equals negative 5 over 2. Because the vertical asymptote is a line, or an imaginary line, that the graph approaches but can never touch. Okay, because the graph itself, the function itself, cannot equal negative 5 over 2. So the graph will approach it on both sides of that, and approach it very, very close. So we know the vertical asymptote. We know what value x cannot equal. And so we can also find another couple things. Not I mean, I'm a visual person, so I like to have a little bit of a visual, like a graph of some sort, to let me know what's happening here. So what I'm also going to do is I'm going to see, well, what is there a y-intercept? So the y-intercept I know is when x equals 0. So if I substitute 0 into this, I get 40 minus 3 times 0 all over 2 times 0 plus 5. So that and that disappears, so I'm just left with 40 over 5, which equals 8. So the y-intercept is 0, 8. I can also find the x-intercept, and the x-intercept is when y equals 0. So if I let this whole rational function equal 0, 40 minus 3x over 2x plus 5 equals 0, well, to solve for x, I can multiply both sides of the equation by the denominator. Like that. And 2x plus 5 over 2x plus 5 equals 1. 2x plus 5 times 0 is 0. So we're left with 0 equals 40 minus 3x. And then I solve for x by subtracting 40 from both sides, and then dividing both sides by negative 3. So I get 40 over 3, which is approximately 13 and a third. Well, it is 13 and a third. It's approximately 13.3. So notice here, even to take a quick shortcut, this will happen all the time when you're finding the x-intercept. When you set the y equal to 0, and then you multiply both sides by the denominator. The denominator disappears from the one side, and it gets multiplied by 0 on the other side, so it just ends up disappearing. So you can actually just take the numerator and set it equal to 0, and then solve for x in that case. So you can kind of have a bit of a shortcut and do that. So the x-intercept ends up being 13 and a third and 0. Okay, so this kind of gives me a bit of an idea of what the graph's going to look like. So if I just draw a rough sketch here, and I don't want to do it too rough, so I'll draw a small Cartesian plane here. So I know the vertical asymptote is negative 5 over 2, so I'll just do that around here. Just assume that that's x equals negative 5 over 2. And I know the y-intercept now is 0, 8, so I'll just say that's around here-ish. And the x-intercept is 13 and a third, so I'll say that's around here. Okay, so from my past work with rational functions, I already now know what one branch of this function is going to look like. If it goes through the x-intercept here, and it goes through the y-intercept here, and it approaches this vertical asymptote, I have a very good idea that this part of the function is going to be curving up like this, and it's going to be coming down here like this. So that's my hunch. And generally speaking, not always, but generally, when you've got a function going up as it approaches the vertical asymptote from one side, it's going to be going down approaching the vertical asymptote from the other side. So it's going to be coming down like this. And there's only one x-intercept, as we found here. There's only one of them. So that means that this part of the graph will not have a vertical asymptote here. So that means that there must be a horizontal asymptote somewhere down below, around here. Okay, so just by finding the vertical asymptote and the y and x-intercepts, I can now do a rough sketch of the graph. What I do want to do, however, is I want to find a little bit closer, a little bit more specifically or precisely, what happens to the graph as it approaches the horizontal and the vertical asymptotes. Now I have to still find the horizontal asymptote, and the horizontal asymptote is found as x gets very, very large. So as x gets very, very large in the positive direction, or as x gets very, very large in the negative direction. So now if I look at this function, if x gets very, very large, this -3 times this very, very large number, that's going to be way bigger than 40. So big, in fact, I can even just ignore the 40. It's like, I always say, suppose it's the kind of the rich man's rule for finding horizontal asymptotes. I always say, well, if a very, very, very rich person, not just a man, sorry, a very, very rich person were to drop, say, a $10 bill out of their pocket, would that loss of $10 bill, or for that matter a gain of $10 bill, will that change their overall wealth to any great extent? And if we're talking about somebody who's a multi-billionaire, an extra $10 will not necessarily affect their overall wealth. So in that case, we can just cross out that 40. And likewise, in the denominator, we can cross out that 5, because those values are not going to make any difference when we multiply this -3 times that huge number and that 2 times that huge number when x approaches infinity. So we can then say, well, then as x approaches infinity, y then is approaching -3x over 2x. Okay? And then we just simplify this, so x's cancel out. So as x approaches infinity, y approaches -3/2. And as I've already shown here, this horizontal asymptote that I roughed in, that's below the x-axis, so that would stand to reason that the horizontal asymptote is y equals -3/2. And as a matter of fact, whether x gets really large in the positive direction or x gets very large in the negative direction, the horizontal asymptote is still going to be the same, because if we have -3x over 2x and x is approaching a very, very large negative number, we still see these x's disappear, which still leaves us with y equals -3 over 2. Okay, so we see the horizontal asymptote. I know that the graph here is approaching the horizontal asymptote from above here, because it has to go through the Y-intercept and the X-intercept here, and then it has to approach the vertical asymptote from the right and go up in that case. I'm just going to double check which way the graph is approaching the vertical asymptote in both directions there, so just bear with me for 1 second as I change pages here. So I'm going to use the same function, of course, and so now I'm going to say, as x approaches the vertical asymptote, -5 over 2, and here I'm going to say from the right, I'll put this little superscript plus to say from the right, then h of x is going to be, I guess, equal, or no, not equal, it'll be approaching. Well, if I put -5/2 into 40 minus 3x over 2x plus 5, I substitute something close to -5 over 2. So remember, if we're looking at the x-axis, if this is -5 over 2, and over here is 0, then that means that if I'm approaching -5/2 from the right, that means that the value of x that's on the right side of -5 over 2, that's going to be larger than -5 over 2. Let's say it's like -4 over 2, just for argument's sake. We just take a sample value just to kind of give us an idea. So if I put in, and that's equal to -2, if I put in -2 here, -3 times a negative, well, that's going to give me a positive. Doesn't really matter what the value is, it's going to give me a positive. And if I put this negative 2 into x in the denominator, I've got a 2 times a negative 2. So the answer is going to be positive here. Well, but that value of x is not negative 2. That value of x is actually going to be closer and closer and closer to negative 5 halves. So it gets closer and closer and closer to 5 halves. That means that the denominator gets closer and closer to 0, which means we have a very, very, very small positive value. And in that case, then h of x is going to be approaching positive infinity because we have a positive divided by a very small positive. Okay, so from the right side, so as x approaches the vertical asymptote of negative 5 over 2 from the right, that means that the function, the rational function itself, is approaching positive infinity. Now if I do the same thing, but now from the left side, so I say as x approaches negative 5 halves from the left, so it's coming along in this direction, then h of x is approaching 40 minus 3x all over 2x plus 5, of course. And that means that the x value is still negative. So if I substitute a negative value into here, it's a negative multiplied by a negative, I still get a positive value in the numerator. And in the denominator, now I've got something that's smaller than negative 5 halves because it's on the left of negative 5 halves. So let's say that could be negative 6 halves, just as a sample. So that's about negative 3. So negative 3 times 2 is a negative value plus 5. That gives me a negative. But it's not negative 6 over 2. It's not negative 3. It's actually closer and closer and closer to negative 5 over 2, which means that this value of 2 times that value of x is going to get, it's still larger than 5 in the negative, but it's going to be closer and closer to 5, which means there's actually going to be a small negative value, which then means that h of x, the rational function, approaches negative infinity. So when I drew this sketch over here, this is now confirmed that the function does go down to negative infinity on the left side of the vertical asymptote of x equals negative 5 halves. And from the right side, it's going up to positive infinity, or approaching positive infinity from the right. Okay, and so that's kind of it for these values, or this function and limits as x gets very, very large. Now the one other little thing, sometimes you don't know, you won't know which side of the vertical asymptote the function is approaching. And so in my experience, you have to kind of have a bit of an idea of what's happening with the function before you begin, or as you're going through it, I guess. And so I know about these two intercepts. I know now that as x approaches the vertical asymptote from the right, the function approaches positive infinity, which means that the function is now going to approach the horizontal asymptote from above. So now in this case, as I was saying, as x approaches infinity, positive infinity, y is going to, I can say y approaches negative 3 over 2 from above. Now the plus sign is being used as from above. So even though the horizontal asymptote is y equals negative 3 halves, that's the actual horizontal asymptote, as x approaches positive infinity to the right here, that means that y, or the function itself, is approaching negative 3 over 2, that horizontal asymptote, approaching it from above. And I found that by knowing that it's going through these two intercepts, and then it has to eventually sort of even out and approach the horizontal asymptote. And by virtue of the function going towards negative infinity as x approaches negative 5 halves from the left, that means that as we go out towards x approaching negative infinity, that means that y is going to approach the horizontal asymptote of negative 3 halves from below. Okay, so we're going to use this negative superscript as from below when discussing when the x values get very, very large in the negative direction. Okay, or I guess from the positive direction, depending on the function. But when we're talking about x approaching positive or negative infinity, the plus and the minus superscripts that accompany the value of the horizontal asymptote will mean from above if it's positive and from below if it's negative. In stark contrast with when we're dealing with x approaching the vertical asymptote from the right and from the left. In these cases, they're actually values that we're using as opposed to infinity. Okay, so that's the end of the examples and description of limits at infinity from section 14b. Can I ask you to please look at examples 2 and 3 on page 349 and let the self-tutor explain some of the finer points of those solutions to you. And then take a quick look at exercises 1 through 3 on page 349. And of course we'll go through a couple examples tomorrow in class, and then you have the rest of the time to work on this material. So thanks for watching, and we'll see you in class.